Okay, so I'm going to be doing the last two lectures in the Machine Learning and Science 2 module on reinforcement learning. Just before I start, I apologize for any loud bangs in the background because there's construction work going on outside my flat. So, in the last module, we very much focused on deterministic reinforcement learning. So, every action determined exactly what state followed next, and the agent always took the same action in each state. But this isn't a very realistic situation, and there are many problems where the environment would be stochastic, include some randomness. So an example of this would be something like playing a board game against a human opponent, because you can't predict exactly what action the opponent is going to take. Or flying a plane in turbulent wind conditions. It's very difficult to predict exactly what the plane will do when you try and control it. Now, obviously, those situations could be made deterministic with sufficient information. If you knew about the exact state of the opponent's brain, or if you knew about all the local wind conditions perfectly. But even if you could get all that information, it would be very difficult to process. And even if you could process it, it wouldn't necessarily be that useful. You could take perfectly good actions and achieve your objective of beating the opponent or flying the plane with limited information. So in those kind of situations, what you end up with is randomness. And that's usually encoded in, is usually theoretically described using Markov decision processes. So we'll begin this lecture by covering Markov decision processes. Then we'll reintroduce values and Bellman equations in this stochastic setting. And then we will cover the techniques that we're going to use to solve these problems in this module, which is using policy gradient. So just to start with, we'll start with MDPs. So as in the last module, we have this decomposition into a environment and an agent, which has a policy, which you use it to take actions. The difference being in this module that the environment and the policy are now stochastic. So obviously, the examples I said before, it's clear that the state should be probabilistic, should be random. But it's also possible that the reward can be random if you're playing like a slot machine in a casino, for example. All you're doing is like pulling a lever and you get a random reward back. You don't have that much control necessarily over what you get. So the environment, as before, sends both the state and reward to the agent, given an action that it's taken. So we now write this as a conditional probability distribution, where we get the next state S primed and the reward R, given some previous state S and the action A taken in it. And to conserve probability, we require this to be normalized. So if we sum over S primed and R, this gives us 1. Now, it can also be useful to consider the agent and its policy to be stochastic as well. And we've already seen an example of this in the previous module, where we used a random behavior policy, the epsilon greedy policy, to encourage exploration. But then we used that as off-policy data to learn a deterministic target policy. So now we're in this probabilistic setting, we can actually just learn a probabilistic policy, target policy directly, which we'll call pi, which predicts the conditional probability, which predicts the probability of the action A given the state S. And we also require this to be normalized. And obviously, the thing that we'll be interested in are full trajectories of the evolution given by these two conditional probabilities. So the trajectories. And these are sequences of states, rewards, and actions. So simply put, if we start from S0, we take some action A0, this leads us to the state S1, we get a reward R1, and then we take another action A1. And this continues until some end time where we receive the final state and the final reward. And for shorthand, we'll often just write this as omega naught t, where this is the set of states, rewards, and actions along a trajectory for an episode. And this capital T, the end time, can vary depending on the end condition of the problem. And obviously in this notation, the first reward and the last action don't really exist. They don't count for anything. So, as before, we need our objective that we're going to optimize. So this is just defined in terms of the returns. And the return is just defined as the sum of the rewards along each trajectory. The R of omega t is just the sum over equals 1 t of RT. And then the objective is simply to maximize the average value of this return over the possible policy. So in order to define this average and to define values, we will need to define the probability of each trajectory. So the trajectory probability is just going to be the product of the probabilities of each state transition and each action along the trajectory. So this will just be the probability of omega naught t given, for example, S0, so the first state is fixed. Then this is just the product from t equals 1 to the final time of each state transition. And the action that led to that state transition. And then using this, we can then define values, similar to how we did in the last course, the last module, but the difference now being that, whereas in the last module, the value of each state was defined by the unique deterministic path that the policy followed after it, now this is given by a sum over all possible trajectories that could lead from that state. So the value of the state under the policy pi is now given by the sum over future trajectories and the actions before that future trajectory. Here I've just replaced 0 with 1, so it's just indicating it's from the next time step onwards, not including the first one. And then we just have the trajectory probability and the return along each trajectory. Okay. So the same thing can be done for state values and same thing can be done for state action values as in the last course, but we won't really be needing them. So I'll leave those to the lecture notes. Obviously, as in the deterministic case, we can define Bellman equations, which tell us how these values are related to each other. So in the deterministic case, what we had was, for example, the value of the state S was related to a particular state, the value of a particular state S primed, plus whatever reward was received in between those two transitions. This first step is given by is choosing the action given by the policy, and then this is the state transition from the environment. So in the stochastic case, we now have to deal with there being multiple possible next states for the Bellman equation. So now we start from a particular state S, and then this could go, so the policy could take multiple different actions in this state. And then from each of these actions, these could go to multiple different states. And the value of S is then given by a weighted sum over all of the values of the S primed, plus the rewards that could be received in the process. So this will then so for example, the Bellman equation relating state values to the values of the next states that could be visited would then be a sum over the actions that could be taken in that state and the next states that could occur and the rewards that could be received, with the policy probability, the environment probability, this would be S primed, are given SA, the policy probability for the action, and then this would be summing over the value of the next state and the reward that was received. So this is just relating values of the previous state to the value of the next state that could be in and the reward that you get in between. So this will be useful later, but we're going to forget values for the time being. The technique we're going to use to solve these reinforcement learning problems in this course is called policy gradients. So in the last module, we focused on evaluating the current policy by calculating its value function, and then using that value function to infer what an optimal policy might be. You can still do this in the Markov decision process setting, but a very popular approach to solving these problems currently is just to instead directly parameterize the policy itself and then optimize the weights of the policy. So we directly parameterize the policy. So, for example, we have pi of theta, where theta are some weights, and those are what we optimize in order to solve the problem. So why would we do this instead? So the advantages of this approach are that, for a start, since the policy is now definitely stochastic, this allows us to bake in exploration from the start into the policy without having to soften the true policy that we're learning, like we did with the epsilon greedy policy. A second advantage is that it allows us to take random actions. And while this might not seem like it's immediately useful, if the environment is varying, it can actually be optimal to have a more stochastic policy. So a simple example of this is something like bluffing in poker. So for example, where you're playing against an opponent which is adapting to how you're playing, the more random you are, the harder it is for the opponent to adapt. So this allows the policy to incorporate things like bluffing. Another advantage is the theory behind policy gradients, and in particular, the stability that this theory shows it has. So in contrast to value-based methods, if I were to have a parameterization of the value function and be basing my policy off of an epsilon greedy version of choosing the action which has the highest value, if I change the weights very slightly and suddenly the action which is the optimal, which is the highest value changes, the policy changes dramatically. And as such, all of the true values change dramatically. And these sharp changes can induce instability in value-based algorithms for learning and policy. In contrast, if I'm learning to optimize the policy, if I change the weights slightly, all of the probabilities you'd hope will only change very slightly. And as a result, this kind of smooths the whole learning process out. But this also relates to a negative of policy gradients, which is that they can require a lot of data to learn and optimize, and it can take quite a long time because of that smoothness. A final use is that they very easily handle continuous action. So if you were to try and handle continuous actions using a value-based approach where you were picking the action which maximizes the value function, when you try to sample actions from that policy, every time you sample a continuous action, you have to maximize a function, which isn't a simple task. Whereas if you are learning a policy, as long as you set up an appropriate policy, you can very easily sample a continuous action from that policy. So it's much more natural in a setting with continuous action. So to start with these techniques, we need to introduce the loss function. And this is simply going to be, so first we need to define the trajectory probability again in this kind of parameterized setting, just to define notation. So we'll write p theta of omega 0t trajectory is the product over time steps of the environment step given the action chosen by the policy and some initial distribution for sampling the initial state. Then the loss is simply, the loss maybe isn't an appropriate word for it in this situation, since we're trying to maximize it. The loss L theta is the average return over all trajectories under this policy. And since we are trying to maximize this, we'll use gradient ascent rather than gradient descent. Okay. In order to do this, we need to calculate the gradient. And at first glance, it might seem like calculating the gradient of this object could be quite complicated, because the trajectory probabilities are quite complicated objects, but it turns out to actually be quite easy. So to start with, we'll just calculate the gradient of the trajectory probability, since that's where all of the dependence on the policy is. So I have del theta of p theta of the trajectory. And if we go back and look at what this trajectory probability was, this policy should depend on theta here. This derivative is only going to hit the policy for each state in the for each action in this product. And since it's a product, we can split it up using the product rule or Leibniz rule. And then for each action that the derivative hits, it's going to take that action out of the product of probabilities. But we can then introduce a ratio of these probabilities in order to then just rewrite this as still having the overall trajectory probability at the front. And then for each time step, we have the derivative of that policy at that time step. Divided by the policy at that time step. This term on the bottom is just what we're reintroducing a ratio of pi over pi in order to be able to have that trajectory probability at the front of this equation. Okay, and then we can rewrite this equation slightly using the fact that the derivative of a log so for example, del x f of x equals f of x del x log f of x. So we can substitute this into this equation, just rearranging in order to rewrite the sum as a sum over the derivatives of the log of the probability. And if we substitute this into the overall loss, what we get is a sum over trajectories with the trajectory probabilities, the return of each trajectory, and then the sum over time steps of the derivative of the log of the probability of the policy. And this derivative of the log of the policy is sometimes called the eligibility, or the eligibility vector. We'll just call it the eligibility for brevity. And this, oh, sorry, they've gone behind the camera. So the eligibility essentially tells us what direction we need to move the weights in order to increase the probability of that action occurring. So the eligibility is the direction to increase the chance of the action occurring. So the overall gradient then points in the direction that tries to change the probability of each action proportional to the return of the trajectories that those actions occur in. So if it occurs in trajectories which have a positive return, then it will try to increase the probability of those actions. If it occurs in a trajectory which has a negative return, it will try to decrease the probability of those actions. But what this appears to leave us with is an update where the way we're changing the weights depends on the past of the actions. So we're trying to change the probability of an action according to the rewards that came before it, which doesn't make too much sense because the probability, the actions can only influence the rewards that come in the future. So there is a question of like, should the probability change depend on the past? Luckily, it doesn't have to. So sorry, 1 second. So luckily, we can actually remove this dependence on the past because the gradient has an invariance. So to see this, let's see this invariance. What we have to look at is the sum over actions of the policy probability multiplied by the derivative of the log of that policy. And this term, we can use that identity we had before to rewrite as the sum over actions of the derivative of just the policy. And we can take this derivative outside and perform the sum, which by normalization is just 1. So we get the derivative of 1, which is just 0. So we can use this to get rid of the past in the derivative of the loss for each term. So to do this, we first split up each contribution of the return. We have the sum over time steps. And then we split the return into the part which depends on the past. Into the future part and the past component. Sorry, it should be lowercase t at the top and 0 at the bottom. And we still have the gradient of the policy, the eligibility. And then at this point, what we can do is we can use this identity to perform the sum over the probabilities back to the time step of the transition. And then we can sum over the actions to remove the first part of this return. Since the reward at the time step t has no dependence on the action at. Then we can just essentially show that this term, when it averages out to 0, then what we end up with is just the sum over trajectories, sum over times in those trajectories, and the returns that follow each transition in that trajectory. So now what we have instead is a equation for the gradient, which is exactly the same. It has the exact same value as our old equation for the gradient. And the difference being now that this only moves in the direction of the future. It tries to move the weights such that it increases or decreases the probabilities proportional to the return in the future of each transition rather than all of them. So now we can see that in reality, this gradient moves theta proportional to the future returns, which is what we would expect. So how do we use this gradient equation? As I said before, we're doing gradient descent, but obviously calculating the gradient exactly is pretty much impossible, because for a lot of complicated problems there will be far too many trajectories, and calculating their probabilities exactly will be too hard. So instead we'll use stochastic gradient descent. And the way we'll do this is we'll sample a trajectory, and then we'll use that to estimate the gradient. So our estimate for each trajectory will simply be that the gradient is approximately equal to, so we're running the trajectory, we are sampling each of these trajectory probabilities, and then along each trajectory we just want to calculate this quantity, the reward in the future of each transition and the eligibility for each transition. This will then just be, for each trajectory, the sum over time steps of the returns. I'm going to just label the subscript t plus 1, and the gradient of each transition, each action that happened along that trajectory. And then the update, just doing gradient ascent, is simply that we turn theta into theta plus, because it's ascent, some learning rate, and the estimate of the gradient that we calculated, given by this equation up here. So as an example, we'll return to the model we looked at in the last module, which is the excursions. So in these excursions, what we have are a particle with a position, and okay, so we run trajectories with a particle which has a position x, and it moves up or down at each time step. So the state consists of the position and time. So right, S is x and t. And the actions consist of a choice of whether to go up or down at each time step. Up / down. A equals plus or minus 1. And in this case, the environment is deterministic. So if you choose to go up, the state goes up by 1, and the position goes up by 1, and the time iterates by 1. So the environment is simply given by I'll drop the reward in the environment because it's deterministic in this case, and I'll give you that in a second. And this is simply saying that S primed is equal to S plus A. Sorry. X primed is equal to X plus A. And the time T primed is just equal to T plus 1. And our goal is to reach the target at a particular position at a particular time. So for simplicity, we're just going to say that this target is at position 0 at time capital T. And we're going to stay above x equals -1. So we want to be at 0 or above. Our goal is to have trajectories that look something like, if this is the position time, we'll start from 0 and want something which looks perhaps like this, where this is the target time. And we do this by having a reward which is shaped to encourage this. So what we do is that this is a function of the state afterwards, the action, and the state before. And this is going to be given by minus the modulus of x, so you get more of a punishment. As this is for when the next state is at some position and the final time. So you get more of a punishment the further away you are from the target. And then we'll have minus c of mod x for earlier times when x is less than 0. So you get more of a punishment the further below 0 you get. And C is just a way of making the agent prioritize staying above 0 or hitting the target. And then we have 0 otherwise. So the way that we do this is using a tabular approach, just for simplicity. So that is to say that we have a tabular policy. And in this approach, what we do is we associate one weight to each state. We have one theta of x and t for each state. And then to get a probability distribution out of this, we use a sigmoid. So the probability of going up, pi of 1 given x and t, is simply going to be the sigmoid function on this potential theta of x and t. So writing that out, that will be the exponential of this weight divided by the exponential plus 1. And then the probability of going down is simply 1 minus this. So in this case, the eligibility is simply given by we do the derivative of plus or minus 1 with respect to the weight. Just for completeness, we'll have this weight be at a different, at some arbitrary position. And then what we get is plus or minus 1. The Kronecker delta of the position. So obviously the weight has to be, the weight you're doing the derivative with respect to has to be the weight associated to the policy that you're doing the derivative of. The same for the time. And then you get the probability of the opposite action. So since we've got these Kronecker deltas, the derivative of the policy with respect to each weight is completely independent for each site. And because of that, we can then, rather than constructing this whole big update to the weights by combining these eligibility vectors with the returns that follow them for each state, we can just apply the update to each state's weight individually. So there's code demonstrating that online. And then when we do this and apply it to this problem, what we get is, just come over here. Okay. So what we have here is just on the left we have sample trajectories of the with the current policy. So the black lines are the original policy, which is just 100% 50-50 random, and the blue lines are the learned policy at the end. And the right graph is the an estimate of the return for the policy at each step during its learning process. So some people call this a learning curve. And then in the text on that graph, it shows you the average return for the original policy and the average return for what we learned. And for reference, completely optimal is obviously just 0 because it gets no punishment. It just generates the correct trajectory every single time. And it's getting pretty close to 0. And it does it relatively quickly. It gets most of the way there in around 150 episodes. So it's not doing too bad. But generally speaking, this method is quite slow, especially for much more complicated problems. And the reason for this is because of the high variance of the returns. If I run a load of trajectories for a very complicated problem, I have completely different trajectories after taking the same action in the same state every time. You can get very different returns, and this can cause a very high variance in the estimate, and that can slow the learning process. So it's slow because of high return and the high variance in the return. So the way we're going to solve that in the next lecture is to reintroduce value functions in order to first contrast these returns with what we would expect the return to be on average, and then to eventually replace those returns. And then hopefully afterwards we'll go on to covering a little bit of deep reinforcement. Okay, thank you for listening.